Welcome to Study Loop.
Hello everyone, today we're doing chapter 23, problem 74, and this problem asks us to determine why is HA so much less acidic than HB and draw the mechanism for the reaction. So it's saying HA is less acidic than HB, and what do we know about acidity? Well, the stronger the acid or the better the acid means that the more stable its conjugate base. So let's look when we deprotonate HA versus HB. So when we deprotonate HA, what are we left with? So we deprotonate HA, we're left with a carbon anion at this carbon. And now, if I want to do a resonance structure, I actually can't do any resonance structure because there's already there's already a pi bond here, being an sp2 carbon. So because of that, no resonance structures can be formed to place a negative charge on the oxygen. So there's actually no resonance structure that can be formed with this, making this charge localized solely on this carbon nucleus and unable to delocalize around the ring to more electronegative atoms like this oxygen. So let's look at HB though. So if we look at HB, so HB now, so deprotonating HB will make an anion here, in which this can go through resonance structures such that it can make a pi bond here, making a new bond. You make a bond, you break a bond. So this pi bond will go here, making a new bond. You make a bond, you break a bond. So the carbonyl bond will break, delocalizing this lone pair or delocalizing the lone pair electrons onto the oxygen nucleus, which is very favorable. So because this lone pair electron of this carbanion was able to delocalize around the ring to the oxygen nucleus, it stabilizes this conjugate base by resonance much more than when HA is deprotonated. Therefore, when removal of HB will generate an enolate that delocalizes onto the oxygen nucleus. However, removal of HA with base generates an anion that cannot delocalize onto the carbonyl oxygen. Therefore, it makes it a very hard and a strong charge that is unable to delocalize, therefore decreasing the stability of its conjugate base. So that's why the deprotonation of HB is much more favorable and making this one a more acidic proton than HA. So the mechanism of this reaction to add this alkyl group onto the least acidic proton on this molecule actually involves some sort of resonance. So let's work through it. So we know that addition of base is going to deprotonate the most acidic proton. That's going to be HB. So after we add base, so in step 1, we're going to deprotonate HB. That's going to be ripped off. So we have a lone pair electron here. Now with this lone pair electron localized on this carbon nucleus, you're going to have a resonance structure that makes a new pi bond here, making a bond. When you make a bond, you break a bond. So now your pi bond electrons will be localized onto this carbon nucleus. So you have a lone pair electrons here, a new pi bond. And now this can act as your nucleophile to attack this electrophile, doing a backside 180-degree attack at this carbon, making a bond. You make a bond, you break a bond. So I had a 1, 2, 3, 4 carbons. So now we need to regain the double bonds at their original position. So what we can do is, now with our Br minus that fell off, we can use this to now deprotonate the alpha proton here, making a bond. You make a bond, you break a bond, so you form an original original keto alkene bond here. When you make a bond, you break a bond. So this is going to go through this nucleus and attack that water that's being added to protonate it to now form your final structure, which is seen here.